All right, so this is the formula for area, finding the area. So basically what we're doing, if we had this, you know, something like this little portion of a rose that we were trying to find the area of, we would find the radial lines are like these lines that bound. If I were to draw these radial lines here, between here and here, this would be like my alpha to my beta. And then I'd have the function that represents this part of it. But the alpha and the beta are just, you know, what angles it's going to take to graph it. Is it from 0 to pi over 2, or 0 to pi over 4, or negative pi over 2 to pi over 2? In other words, what would be your range that you have to put in the calculator in your window to graph just that one section? And so that takes a little bit of time. The hardest part of the area ones is usually finding the alpha and the beta, unless they give it to you. The idea here is we're basically splitting it up into a bunch of little radial lines, and we're just finding the area. It's kind of like estimating a bunch of these little pieces of a pie that we're doing. Instead of adding up rectangles like we did, this formula is based on adding up slices of a pie, since we're dealing in a circular coordinate system. All right, the next one is the formula for arc length. And this is theorem 10.14, arc length. In polar coordinates. Now, you've had area formulas before. We did area between two curves before, where we subtracted the top and the bottom functions, or the left and the right functions. We've done arc length before, but not in polar coordinates. These formulas are based upon the fact that you have an equation that is r equals something with theta in it, rather than x comma y. All right, so the arc length, very similar as far as the explanation. I'm just going to give you the formula. So s, little s is arc length, is the integral from alpha to beta of the square root of, I'm just going to give you the easiest version, r squared, okay, your r function, plus the derivative, dr over d theta, the derivative of r in terms of theta squared, d theta. And that's going to give you the arc length. And then the surface area, in polar coordinates, okay, the surface area in polar coordinates, there's two of them. The first one is about what we call the polar axis. We'll talk about that too. About the polar axis, capital S equals 2 pi times the integral from alpha to beta of f of theta sine of theta square root of f of theta squared plus f prime of theta squared d theta. And this is about the line theta equals pi over 2. That's the second formula. And that's S equals 2 pi times the integral from alpha to beta. And this time it's just f of theta cosine theta, the x part, square root of f of theta squared plus f prime of theta squared d theta. All right. So now let's look at some examples. So these are the formulas that you need. They're all in the book too. So, yes?
Second one, is it always about line pi over 2, or does that change?
The second one?
Yeah,
It's in the polar coordinate system, it's always, it's like you're taking the polar axis. The polar axis is like the axis that goes left and right.
Yeah.
And the line theta equals pi over 2, isn't the angle pi over 2 this one that shoots straight up, the y-axis? So the polar axis is really just the x-axis, and the line theta equals pi over 2 is like the y-axis. That's really all it's saying.
What if you want to use it, or do you not ever do that?
You don't ever do that. It's like if you did, you'd have to subtract the function from that line, that radial line. It'd be a line at an angle, and we don't do that here. That would be a higher level calculus class. All right, so example number 1. Find the area of one petal for r equals cosine 2 theta. Find the area of one of the petals of r equals cosine 2 theta. All right, so first thing we have to do, we have to look at the graph of this. Okay, now I'm going to hit my window. I've got it from 0 to 2 pi. I'm going to graph it, and I just want to see what it looks like. Whoa. Okay, now that should be better. Okay, it looks like I have 4 petals there. Okay, so I probably want to change, that's from 0 to 2 pi. Okay. So maybe I basically need to figure out, okay, I'm using the formula. The area is going to be 1/2 the integral from wherever to wherever I choose to give me one petal. And it's my r function. Okay, my r is cosine of 2 theta, and I just need to square it. So it's cosine 2 theta squared d theta. So all I have to do is figure out what are my limits of integration. I mean, the formula is easy to use. You take your function, your r equals, you square it, you put 1/2 in front of it, but now we need to just mess with that. We need to mess with the window. Let's say I go from 0 to, I mean, does it make sense? There's 4 petals. 2 pi divided by 4 would mean one petal takes how long to get to? Pi over 2. So let's see if we go from 0 to pi over 2, if that just gives us one of the petals. Nope, it doesn't. See what it does? So we can't just go from 0 to pi over 2, but does that seem like, would those two things, like if, wouldn't they give us a full petal? Does it, pi over, okay, but instead of starting from 0 to pi over 2, maybe where should we start?
Pi over 2 to 3 pi over 2. Pi over 2 to pi.
Pi over 2 to pi?
Yeah.
Okay, so we're going pi over 2 to pi. Now if I graph it, oh, nope, it's still one of those just halfway things. Pi over 2 to pi over 2? Oh, you want to try negative pi over 2 to pi over 2? Okay, we'll try that. This trial and error here. Ooh, that's more than 1. Any other ideas? No, that's more than 1 petal right there.
Can you do like
I mean, that's kind of cute, isn't it? It's like a fish with a fancy tail. Or like an octopus from the side. What? Squid? Okay. What do you think, what should the window be? Negative pi over 4? Remember we said the length should be pi over 2? Negative pi over 2 to positive pi over 2 is how long? Pi. So that was twice as long as we needed. So then we graph it, and there we go. We've got that's right. I don't know. What is the deal here? Yours does that too?
Yeah, mine does too.
It's right. I know it's right. So we're going to go from negative pi over 4 to pi over 4. Could I go from like pi over 4 to 3 pi over 4 maybe?
Yes.
I mean, you can do window. Let's go from second pi divided by 4 to 3. Guys, are you with us?
Yeah.
Okay, this time I just went pi over 4 to 3 pi over 4. There, that one's beautiful. Okay, so I like that better. I'm going to go from pi over 4 to 3 pi over 4 just because my graph turned out nice. If you went from negative pi over 4 to 3 pi over 4, it's probably going to work out the same. Okay, what are we going to do from here to find the antiderivative? We're going to use the calculator. We're going to hit math. Okay, we're going to hit math, and then we're going to go down to function integrate. And we're going to go from second pi divided by 4 to 3 second pi divided by 4. We're going to hit begin parentheses, cosine 2 theta in parentheses, end parentheses again, and square it. And then your d theta, and hit enter. And what do I need to multiply that answer times? Times 0.5. And I divided by foot. And the answer is 0.3927.